Hello everyone, and welcome back to our 6th webinar on SEMLA, software engineering for machine learning applications. For those of you that you have followed us from the beginning, we have had 5 very interesting webinars so far from Ben Schneiderman from University of Maryland, Vera Liao from IBM, Misha Talagala from Pixeta, Danilo Sato and Arif Wider from ThoughtWorks, and Ying Dong Tang from Microsoft. So today we have our last but definitely not least webinar for the SEMLA series by Grace Lewis. So Grace is from Carnegie Mellon University, from the Software Engineering Institute, where she's a principal researcher and the lead for the Tactical and AI Enabled Systems initiative. She leads 2 very interesting projects, namely characterizing and detection mismatch in ML-enabled systems and predicting inference degradation in production ML systems. Among other roles, she also holds important positions in IEEE and IEEE Computer Society. So we're very excited to have Grace with us today, and she will talk to us about challenges of ML-enabled software systems with respect to security and design. So the main motivation is that machine learning components are still software components, but what we may not 100% understand at the moment is that they pose certain challenges in architecting intelligent systems and designing said components. So I won't say much more, because I think Grace is the most appropriate person to shed light on these questions, and I will let her continue, not before remind you a little bit about the logistics of the webinar. So during Grace's talk, you can feel free to pose your questions through the Q&A functionality of Zoom. So all the questions will appear under the open tab. So you can pose your questions there. Also, you can vote for questions you agree and you like. So we can also avoid duplicates. And then I, as a moderator, will relay the questions back to Grace based on the time they arrived and the popularity. So without further ado, I will pass the screen sharing to Grace so she can start her talk.
Okay. Thank you very much, Marius. Always a pleasure to interact with all of you. I will go ahead and get my screen started, and that will start my talk. Can I simply get a confirmation that it's all working?
Yeah, I can see the screen.
Okay, perfect. Well, thank you very much, Marius, and to the team for inviting me to talk to you about architecting ML-enabled systems. The observations that I'm going to share today, because they're really just observations, are based on several engagements that we've had with industry, in addition to working sessions with practitioners and researchers in the field. So with that, I'm going to go ahead and get started. If I can get this working, perfect. So what is the motivation for this talk? And Marius already shared a little bit about the particular motivation. Is that, first of all, yes, that it is absolutely correct. ML components, in the end, no matter how they're developed, they are software components. But they do have certain characteristics that create challenges and unique quality attribute concerns from an architecture perspective. First of all, and this is something that I definitely don't need to explain to this group, is the fact that of their data-dependent behavior. The fact that their behavior depends on the data that the component is trained with. Because of this, the other unique quality concern is the need to detect and respond to drift over time. Because an ML component, its behavior depends on the data that it was trained with. If the data that ML component is encountering in production does not match that data that it was trained with, then this leads to drift. And from a systems perspective, we need to be able to detect and respond to this drift over time. And in addition to that, in order to retrain the model, we have to capture new data, and we have to capture ground truth for that data. So also, in addition to that, being able in a timely manner capture that ground truth that informs retraining is also a somewhat unique characteristic of these types of systems that really needs to be analyzed from an architecture and a system perspective. So the bottom line is that architecting systems that incorporate ML components, in particular, because of these unique characteristics, we really have to think of those, again, from a systems perspective. So the observation number one, and again, shouldn't be a surprise to this group, is that while much attention really has been paid to model development and evaluation, much less attention has been paid to putting models into production, and in particular, model maintenance and evolution. So that's my first observation. This diagram is going to seem very similar to those of you that are familiar with the very well cited Amershi paper on software engineering for machine learning, a case study, which talks about how models are developed at Microsoft. But we adapted this. We adapted this because even that paper, which is an extremely good paper, it leaves out the model maintenance and evolution. So for adaptation purposes, we added this particular step right here, because that is something that needs to be considered from the start. Because sure, you monitor a model, you capture a lot of data about that model, and at some point, the monitoring system is going to say, hey, something is not going well here. We need to retrain this model. And so we call out an explicit model maintenance and evolution step that really looks at how the data is changing, and at this point of time, we need to make a decision. We need to decide, okay, is it the data that's drifting? Am I seeing different distributions in the data, which leads to what we call naive or iterative retraining, which basically means I have to go back to the data engineering step. I need to capture more data. I need to look at the data that I have, et cetera. But if we're looking at problem drift, which means that it's not the data that's drifting necessarily, it's just the problem space that is drifting, then that's a whole different issue, because now we need to go back to model requirements and see, okay, what is it that is happening? How is the problem space changing? Because that may dictate the development of a brand new model. So this model maintenance and evolution step is something that really needs to be considered from the start, because it informs the architecture, not only from a monitoring perspective, but also from a retraining of the model itself and how it has to go back into production. So the observation number two, and again, this diagram should be very similar to those that are familiar with also the very well cited Scully paper on hidden technical debt, is that what is claimed in this paper, and it's something that I 100% agree with, is that little black square right here that is not very legible, it says ML code. And basically what we always need to remember is that ML components are parts of much larger systems. In order for a model to perform well, it needs a whole bunch of other components around it. And this is once again why we consider that software architecture, it's a very, very important activity when it comes to developing these types of systems. The third observation that stems from this need for model monitoring and evolution, and this need for understanding all of component dependencies, is that we strongly believe that software architecture cannot be an afterthought. Developing, maintaining, and evolving these types of systems requires architecture thinking because of the two prior observations. And I'll come back to these observations at the end. So what we define is what we believe the role of software architecture is in the development of these types of systems. Okay, for some reason it's not advancing. Here we go. So we believe that there is a need for a centralized planning and software architecture activity when we're thinking about developing these types of systems. We start from business context and system requirements, which is very typical of any system. And then we go into a planning and software architecture step. Out of this planning software architecture step is going to come the need for three different types of components. And we have to plan and design for these three different types of components. So starting with the red in the middle, some of the components of the system are going to be traditional components, right? We develop them in a traditional way, which is some combination of low-level design, implementation, and quality assurance. And once we're done with that, call it cycle, call it iteration, call it sprint, call it whatever. Out of that process comes a software component, one at a time as planning and software architecture is done. Looking at the bottom, then we have ML component development. So during planning and software architecture, a decision has to be made, okay, to satisfy this requirement, we're going to have to develop a machine learning component. And that life cycle is a little bit different because it matches the two previous slides. So we have to, it's a very different cycle. One of the things I'm going to talk about later, it's a very different pace. But once the iteration or cycle or sprint, whatever, for this component is ended, then at the end, what comes out are two main components. One is the model itself, and the other is a data pipeline component. And we'll talk about co-architecting at the end. And then, and this is where I believe the largest difference is because of the data dependent nature of machine learning components, we have to think of monitoring like as a top quality attribute, which is one of the things I'm going to talk about later. And to me, this is the largest difference, that when we're doing planning and software architecture, we also need to think about these types of components of infrastructure and platform components that are going to provide the information that we need to be able to detect and respond to drift. And so what is going to be part of this infrastructure? Things such as governance or regulatory compliance, also because of the data dependency and maybe privacy issues and things like that, monitoring and management, key type of components. Any requirements that the platform needs to satisfy in terms of scalability and security, not only for the machine learning components, but for the system as a whole, and also deployment and automation, because one of the things that we also, or an end goal for these types of systems, is to shorten as much as possible the training retraining cycle, so that once a model is no longer performing adequately, that we can quickly get all the information back to, for example, a data science team to be able to quickly produce newer versions of that model that respond to changes in either data drift or problem drift. So then what is observation number 4? Observation number 4 is that a centralized planning and software architecture activity is going to ensure that issues encountered in all the development activities of those 3 teams that I talked about before are centrally discussed and propagated to all development teams. So we basically believe that in these types of systems, it is the architecture that is the unifying force or the unifying medium for all the issues encountered by these different teams that often tend to have different perspectives and also concerns. So then, which brings us to observation number 5. During the introduction, one of the things that Marius talked about was one of the projects that I've been working on, which is characterizing and detecting mismatch in machine learning systems. If you're interested, the link is included below of that paper. But using software architecture design as the centralized activity also helps to address mismatches that occur because you have 3 different types of people with often 3 different languages, 3 different backgrounds, 3 different concerns, developing components of the system at the same time. And so using software architecture as a central activity also helps to get these 3 perspectives into alignment, which is also very important for avoiding mismatch once machine learning systems are put into production. I'm going to do a check, Marius. Any questions so far? Because this would be a good stop point.
No, not so far from,
okay.
From the audience.
Okay, perfect. Thank you. So given that background, given that premise, given that motivation, we've identified, like I said before, based on several industry engagements, as well as sessions with researchers and practitioners, a set of challenges, but also opportunities, because always where there's a challenge is an opportunity when it comes to architecting machine learning systems. There is a challenge and opportunity in developing software architecture practices for machine learning systems. That's kind of like the overarching challenge, right? That would be like the end goal. But one thing that I would like to notice, and I'm going to go deeper into each of these challenges, is that a lot of these software architecture practices and ML systems are going to be associated or satisfy a need related to these different, like I would call them sub-challenges. One is that we need to develop architecture patterns and tactics for what we call ML important quality attributes. We need to think of monitorability as a driving quality attribute because it's essential for these types of systems. And we need to think about 2 concepts that we've been calling co-architecting and co-versioning. And I'll get to those in a second. But the software architecture practices that we develop as a community are really going to be driven or going to rely a lot on these sub-challenges. Okay. So software architecture, again, for this crowd, I think this is a very, very well-known concept, but just in case. So the way we define the software architecture of a system is the set of structures that are needed to reason about the system And that means the software elements, the relationships between these elements, and also the properties of both, properties of the software elements as well as the relationships. And so why do we create a software architecture? Why do we believe it's so important? Because the only way to reason about the quality attributes of a system at design time as opposed to runtime is to develop the software architecture, because it can help us really reason about it and in a way predict them by studying its architecture. So in terms of software architecture practices for machine learning systems, what do we believe is happening and will continue to happen? First of all, we don't need to reinvent the wheel. Many existing software engineering practices and many design paradigms that exist today are applicable to machine learning systems. So any processes for how we develop architectures, any processes for how we evaluate architectures, any processes for how we simulate architectures, those are all going to be applicable to these types of systems because these are systems, right? They're software systems. There are many design paradigms that are going to be applicable to machine learning systems. So any design paradigms from any data intensive system type of system, they're definitely going to apply to machine learning systems as well. So some of these are going to have to be adjusted or will be created, and we'll talk a little bit about this later, to account for this data dependent behavior. Another thing that I think that we need to do as a community is to really define what a machine learning component is, because I think that once we define what a machine learning component is and we reach an agreement on what it means, then we can say, okay, for these particular type of components, and this is what we mean by a machine learning component, these are the practices that apply. This is how they have to be created. This is how they have to be adapted. Sorry. Another thing that we foresee is that some of you might have even been part of these discussions. So the agile development not fans, that sounds wrong, but the community for a long time said, oh, we don't need to do software architecture. Software architecture is not part of being agile. They don't get along. But what happened over time is that both sides started kind of agreeing to, like, you know what, no, you really do have to architect systems, even if you're using agile development. And that led to the concept of agile architecting. And there was an agreement between the two communities of how they both fit together and how aligned. I also see that this is something that is going to happen for machine learning component development, because there does have to be some alignment between current practices and how we architect these systems. In particular, because I think one of the big challenges, especially from a process perspective, is that we know how to develop traditional components. For a traditional component, we know how to define what we call done criteria. It's like, this component is done once it reaches this thing or these characteristics. But machine learning components have a very different type of development. It's very experimental. It's very generate and test. It's very trial and error. And sometimes they just don't align well. And sometimes, and these are discussions that like one quote from one of the interviews that we did as part of one of our studies said that usually, so for example, getting to 80% accuracy is 10% of the time, and getting to 90 is 90% of the time of the development. So it's very trial and error. And like I said, sometimes they just don't align. So that is something that we do have to keep in mind, that we are dealing with two very different development approaches, and those have to be not necessarily aligned, but they have to be coordinated. Finally, one thing to keep in mind once we start developing practices and processes for these types of systems is that these teams tend to be very multidisciplinary, because now we're bringing in data scientists, we're bringing in domain experts, we're bringing a new title that is becoming very popular these times, which is ML engineers. So as we bring all these folks together with very different backgrounds, we have to keep in mind that any practices that we develop have to be communicated in a way that we can, not only that everybody understands, but that we also start creating a common vocabulary between this often very different types of teams with different backgrounds. So that leads me to observation number 6, is that, first of all, like I said before, while many existing software architecture practices and design paradigms are very applicable to machine learning systems, we do have to keep in mind that some of these are going to be adapted for this data-dependent behavior of machine learning components, along with the new concerns of new stakeholders that are part of these very multidisciplinary teams. And like I said earlier, the specifics of these practices, we believe, are going to be codified and driven by the need for three things that I'm going to talk about: the architecture patterns and tactics for these types of systems, and important quality attributes for monitorability, and also co-architecting and co-versioning. So let me start getting into that. So what do we mean by ML important quality attributes? Quality attributes, for those of you that are not familiar with the term, they're properties that are used to evaluate the quality and fitness of a system for its mission goals. Sometimes quality attributes are referred to as system qualities. Sometimes they're referred to as non-functional requirements, but I don't like that definition. But basically, you might know them as system qualities or non-functional requirements. Quality attributes, why are those important to define? First of all, because they drive the selection of architecture approaches, including patterns and tactics. Typically, patterns and tactics are developed around quality attributes. So if you want to promote availability, here are some patterns and tactics. If you want to promote security, here are some patterns and tactics. And also because obviously they define the structure and behavior of software systems. So machine learning systems have what we believe high priority quality attribute concerns. Some of these are newer than others, some of these are different, and some of these will have more architectural consequences than others. So for example, explainability, monitorability, observability, these are quality attributes that are very prominent in machine learning systems, and probably not something that you worried about when you were developing more traditional systems. So those are things that we have to think about, that some of these are just have higher priority or might be new to some. Fault tolerance, security, and privacy, these are very traditional quality attributes, but we also have to keep in mind that they might be different or might have different types of scenarios, I would say, when it comes to machine learning systems. For example, in terms of fault tolerance, something that we're probably in traditional systems, what we're trying to figure out is, for example, if a component goes down, can the system keep on functioning and things like that. Whereas for machine learning system, fault tolerance might be something very different. It might be, look, the component is producing predictions that are totally wrong. So what do we do about this now? So it's different types of faults. Same thing with security and privacy. Again, typical scenarios of traditional systems are going to apply to these systems, but a privacy scenario, for example, that might occur in these types of systems is, for example, the fact that you are trying to collect ground truth as you are executing your system. So how do I need to store this additional data that is coming in, and how do I make end users aware of the fact that I might be capturing data from them in order to be able to label my ground truth? So it's, again, just different scenarios that we have to think about. There are also going to be quality attributes that are really kind of new to these types of systems, or at least things that we never thought about as quality attributes. Things like fairness, things of like unintended bias, things like ethics. So starting to define these as quality attributes, like what does it mean? What does fairness mean from a quality attribute perspective? What does unintended bias mean? What does ethics mean? And from an architectural perspective, more than defining what those quality attribute concerns are, I really think that a lot of work is going to be happening is, okay, let's say that we can, as a community, start defining what these quality attributes mean. But from an architectural perspective, limiting the propagation of unintended consequences is going to be an architectural driver that is somewhat unique to these types of systems, and probably something that we really didn't think about before. So, for example, when somehow a system is capable of detecting that it's not being fair, then what? So, what are the scenarios? How do we support these quality attributes? Okay, and so because of that, so once we better define what these ML important quality attributes mean, then we need to start developing architectural patterns and tactics. And again, I hope we don't have to start from scratch, at least for most of them. I think there are lots of communities that we can definitely leverage. So for example, typical instrumentation, logging, and monitoring techniques, they can really help design for explainability. And I imagine that we can leverage a lot from there. The ETL community and patterns have existed for a long time. ETL, extraction, transformation, loading, very typical in data intensive systems. We should be able to analyze these patterns in the context of very specific scenarios. I'm a big fan of scenario driven design. to determine, for example, how these could be extended for any new or different monitorability and observability requirements, and also more established patterns, like, for example, privacy patterns. If you go to privacypatterns.org, it's a very, very nice catalog of privacy patterns. So again, we should be able to look to these communities and just analyze and say, okay, are these enough to address ML system privacy concerns, or can we do some adaptations or some extensions so that they start addressing things that are typical in these types of systems? So I do believe that we are going to be able to leverage a lot of the existing patterns in the community, but there are some that are probably going to have to be developed from scratch. So for example, less studied quality attributes, like I said before, like fairness and ethics, I think these are going to have to be developed from scratch, because it's not something that has been thought about as a quality attribute. Like, how do I promote ethics in a system? How do I promote fairness in a system? I think that these are probably going to be developed from scratch. Sorry, okay. Okay, so along with patterns and tactics, we also need to look at metrics. So obviously, when we're looking at evaluating architectures, and for example, we're trying to say, okay, is this architecture better for promoting availability, or is this architecture better for promoting performance? We have to use some kind of metric. So that we can, for example, say this architecture is better at promoting availability because in this architecture we predict this metric to be X, while in this architecture we predict this metric to be Y. So obviously, metrics for quality attribute evaluation are going to have to be revisited in the context of this system. Not only for the new ones, right? So for example, again, this is something that I think about a lot. So is this architecture more ethical than this one? What is that metric that we're going to use to do that? Or is this architecture, does it promote fairness better than this one? I don't know what the metrics are for that. So not only do they have to be revisited in terms of creating new metrics, but also they really have to be revisited. So for example, in machine learning systems, data quality. So data quality is a metric that is very common in the context of data intensive systems. But in machine learning systems, it has many aspects. So because we have to look at, when we look at data quality, we have to look at data quality in terms of the training data. So what is the quality of the training data? In terms of data drift, what is the quality of the data that is coming into the system that is potentially driving data drift? What is the quality of the retraining data? So once we decide that a model has to be retrained, how do we determine that retraining data is of high quality? And in our systems, how do we promote or put into place practices in architectural elements that ensure that retraining data is going to be of high quality? And I'm sure there are lots of other aspects that we have to think about, but even data quality is something that would have to be revisited in the context of machine learning systems. Conventional metrics also have to be assessed in the light of machine learning systems, like for example, latency, availability, reliability. These are quality attributes that have very established metrics in the community. And it would be useful to say, okay, does latency mean the same for a machine learning system? Does availability mean the same for a machine learning system? And also related to those. And also related to these metrics, I think we can expect machine learning system specific architectural bad smells. Those are likely to emerge as a consequence of this. And as we start creating patterns, we're likely going to start creating anti-patterns, and those are likely going to be tied to architectural bad smells. So this leads me to observation number 7, which is that the development of architecture patterns and tactics for machine learning systems is going to be driven by ML important quality attributes such as explainability, monitorability, fairness, and ethics. Which also leads me to observation number 8, is that if we think about how architecture tactics and patterns have been developed over time, they have been developed based on observation of lots of systems. They have been developed based on observations of how architecture decisions have been made in the past, what are common architecture decisions that are made, et cetera. So if we are going to start developing architecture tactics and patterns, which I strongly believe that we should, and we are, we really need to start sharing common ML design system challenges. We need to start sharing examples that we, for example, that we can mine to look for what are these common design decisions? How are people applying patterns? How are people applying tactics? And that is really going to help us create that, because unless we have a good repository of design decisions and systems that we can mine and analyze for this, well, we're really never going to get to defining patterns and tactics. And this is also obviously, once we start doing that, we should also start gathering, how are people measuring these quality attributes, in particular the newer quality attributes. So creating this shared knowledge is also going to be important in creating architecture, tactics, and patterns for these types of systems. With that, going into the next one, which is monitorability as a driving quality attribute. So obviously, like any other system, there are existing techniques for monitoring systems and infrastructure that are going to be equally important for these types of systems. So measuring performance in terms of system performance, not model performance, measuring resource consumption, detecting faults. Obviously, we will be able to leverage all that, because obviously, like I said, machine learning components are just one type of component in the system. However, monitoring changes in data and how these changes in data affect the rest of the system, it does add a level of complexity that I would say we're not used to when we develop traditional systems. And this is complexity both for the ML components themselves, but also the resulting machine learning system. So when we're architecting these systems, we think about, okay, we're going to put in the model into production. What are all these components and infrastructure that we need to build around this component to be able to detect that model performance is degrading, and what happens next? The other thing that we have to think about is components that incorporate user feedback or any other type of information for ground truth. So to give you an example, like what do I mean by user feedback for ground truth, and how it's different for different types of systems. So for example, let's say this is a very typical example, but there's a system that is a shopping type of system, like shopping at Amazon or any other place, right? So obviously, once you buy something, there's a machine learning component that says, oh, because you bought this, why don't you look at these other things right here and decide if you want to buy? So if I don't click on anything, right, that has to be recorded somehow that perhaps the connection between these two types of products is not good. But if I click on it, then also that means, oh, cool. That means that these, when tying this particular product to this particular product is a good thing. So that is what I mean, but that is, in case it's not clear, that's what I mean by ground truth. But then my system has to be prepared to be able to gather that user feedback and to be able to tie it back to the retraining process, so that we can say this connection good, this connection bad. And so again, that can't be an afterthought. I really have to think about that from the beginning. And it's something that, at least in our experience, we aren't seeing this thinking being put into these systems as they're developed. And so once I gather also that ground truth, I really need to think about, okay, I have this ground truth. How do I feed this back into the retraining process? And also, let's think about adaptations as well. So for example, let's say that at some point I decide, wow, this component is really, its performance, it's really not very good. It's degrading. It's not really matching something or other. What is the adaptation that I need to trigger? Am I running some type of ensemble system where I say, okay, it's time to replace this component with this other component? Or is it so bad that I really just need to stop the machine learning component because something is very critical here, is not going to happen? So again, thinking ahead of all this in terms of scenarios, like I said, big proponent of scenario-based development, is something that we need to start thinking about and start creating scenarios for monitorability. And it should be like, to me, it should be like the top quality attribute for these types of systems. So what challenges and opportunities do I see here? Definitely understanding what different monitoring techniques I'm going to need for data quality, for model quality, for software quality, for service quality, all are different. So I'm understanding how those monitoring techniques are going to be implemented for these different types of qualities, That's what I think is, like I said, a big challenge and opportunity. And another challenge that I think is really interesting, and it's something that was already started to be explored in this paper that I'm quoting at the bottom, that was recently presented at an ICSE workshop, at the last ICSE workshop by Muccini and Karthik, is this relationship between monitorability and self-adaptation. Because if you think about it, there are three types of self-adaptation that really could be either leveraged or would support self-adaptation machine learning systems. So you can think about self-adaptation of ML, which is basically that ML models self-adapt to system changes. And if you think about what MLOps is targeting, this is exactly what MLOps is targeting. You can think of self-adaptation for ML, which is that the ML system adapts to changes that affect quality of service. So I'm not talking about the model here, but of the system. And then you can think of self-adaptation by ML, which is that the system uses machine learning techniques to adapt. And some of this research is already happening in the self-adaptive systems community, which I know is a very active community in Canada. So definitely that relationship is something that we all should be exploring, because it's a very interesting relationship. The other challenge and opportunity is that a lot of the times when people complain, no, not complain, when people state challenges of machine learning systems, it's like, oh, it's uncertainty, it's very difficult to handle this uncertainty, or, oh, it's impossible. Okay, get it, I got it. Yeah, there is inherent uncertainty in developing machine learning systems that contain machine learning components. But the key really is monitorability. I mean, if we accept the fact that there is uncertainty, then let's monitor these systems to be able to detect when things are happening, and to be able to account for this uncertainty, and to be able to compensate for this uncertainty. So definitely that relationship between uncertainty and monitoring, I think, is a good thing that we should do and we should look more into. So observation number 9 then is that monitorability as a driving quality attribute is one of the main differences between machine learning systems and traditional systems. And in the past, when I've been asked the question, so what do you think is the #1 difference? This is typically my answer. I think it's really this need, almost like a mandatory need for monitorability. Which brings us back, and I think we're doing well on time, which brings us to these two concepts that I want to share with you. One is what we're calling co-architecting, and the other one is what we're calling co-versioning. So if you think about it, a machine learning system really has two architectures, not just one, but it has two software architectures that equally, in my opinion, need to be developed and sustained. You have the architecture of the ML system that uses the ML components, but you also have the architecture of the system that produces the ML components. So some people call it the model development pipeline, whatever. And to be honest, this is often neglected. Why? Because typically the development of machine learning components doesn't have the rigor that the development of machine learning systems has. And this is often neglected for many reasons. And so what we would like to propose is this concept of co-architecting. That means that both architectures need to be developed in sync in such a way that design decisions are driven both by system requirements, but also model requirements. So we need to think of these two architectures as two architectures that need to exist. So in order to do successful co-architecting, what is that we need to do? We need practices that enable the synchronization and integration between these two architectures. You need to think about architecture representations for machine learning relevant concerns. So how do you represent, or how do you annotate, for example, diagrams and views and things like that to indicate data quality requirements or model accuracy requirements? And also, how do you represent ML relevant components? Like what is the proper notation for data pipelines, and what is the metadata? What is the proper notation and metadata for model elements? So those are things that we need to think about. And as we're thinking about co-architecting, again, we once again need to think about the fact that machine learning systems are typically developed by multidisciplinary teams. So any architecture views that we create that are kind of specific to these types of systems, they have to be able to reflect and communicate design decisions related to, for example, things like data and feature engineering. And we have to think about the different consumers of these new architecture views. So this is what we mean by co-architecting, the fact that you really need to think about not only one architecture, but two. And then co-versioning. So what we mean by this is that versioning is extremely important in these types of systems. So if we're looking at the machine learning system, I need to know exactly what version of the machine learning component is integrated into the system. That is something that is very important. From the perspective of the machine learning component, because it's so data dependent, once I decide that this machine learning component X is the one that is going to be deployed, I have to have a very clear way and designation to say, this machine learning component was produced based on this data set with these parameters, and I evaluated it with this data. And when I evaluated it with that data, these were the results that were produced. So being able to tie those things together and providing the traceability from the data to the model to the system is what we call co-versioning. One term that we started to use, which we borrowed or stole, whatever you want to call it, from one of our an interview that we did, is that in this organization they call these model packs. So a model pack is something that ties it all together, that is able to provide the traceability and also like the togetherness of all these four things that I mentioned. So what do we require? What do we require to be successful at co-versioning? We need better tools and processes for experiment tracking that better incorporate versioning concepts and tools. So for example, a lot of, and nothing wrong with this, but I mean, a lot of model development is done in Jupyter notebooks, and that's great. I mean, that's a great way to develop models, but it doesn't have the rigor that I'm talking about when I mean co-versioning. For example, if we want to keep track of data sets and things like that, well, GitHub is not a good tool for that, right? Because we're talking about lots and lots and lots of data. So we really need better tools and processes to be able to provide this traceability between these things, between data, models, parameters, evaluation data sets, and results. Another thing that I think is going to be interesting and necessary for co-versioning is that there are lots of proposals out there for, this is how you should document data sets, this is how you document models. Many of you have probably heard of the very famous data sheets for data sets by Timnit Gebru, or this paper called Model Cards for Model Reporting. Great metadata, but my criticism of this, and this is just because this is not a criticism to the quality, but it's to the scope, is that they're very focused on the data science perspective. And I really think we need to extend this metadata to include things like system configuration parameters, test cases, computing resources requirements, because this is something that could eventually be part of these model packs as well. So not only the idea that you're tying the four things together, but you're also including additional data that can help a person that is trying to deploy a model into production to have the information that they need. So this leads me to my last two observations. I wanted to have 10, but I ended up having 11. So observation number 10 is this concept of co-architecting, and that as an ML system has two software architectures that have to be developed and sustained in sync, such that the design decisions are driven both by system and model requirements and the perspective of the different teams that, like I said, tend to be multidisciplinary. And observation number 11 is this idea of co-versioning, which is that when you do versioning machine learning systems, you need to be able to provide traceability from the training data set to parameters, to model, to evaluation, to results. And one way of doing this is using this concept, like I said before, of model packs as something that brings all these things together. So with that, I have reached the end of my talk. And I would like to summarize the talk based on the observations. So first of all, one is just an observation that there is very limited focus in this community on model production readiness. We're kind of still in the model development and model evaluation, and really haven't really focused on model production readiness. The second one is that we need to realize that machine learning components are part of much larger systems. They're not meant, or they shouldn't be thought about standalone things. Because of these first two observations, machine learning systems require architecture thinking. We proposed using architecture or architecting as an activity, a centralized activity that provides alignment alignment between different teams and different perspectives, and therefore reduces the potential for mismatch between teams. Because of that, we need to think about developing and looking at existing software architecture practices and design, and evaluating them and adapting them to be able to apply to these types of systems. Things that are going to be happening soon, I believe, first of all, is we're going to start seeing more and more architecture patterns and tactics for ML important QAs. But like I said before, one of the things that we have to, a precursor to this is the fact that we need to start sharing common ML system design challenges, decisions, and evaluation metrics, because this is, in at least traditionally, how patterns and tactics have been developed. We have to start thinking about monitorability as a driving quality attribute. And like I said before, to me, the #1 differentiator. We have to embrace the concept of co-architecting and pay as much attention to the system architecture as to the ML component pipeline architecture. And finally, co-versioning as very key for end-to-end traceability that is going to be able to enable better reaction to problems that are encountered in production when a system says, oh, this is not, model is not performing well. This is what is going to be enable us to go back to, how was this model created, and let's look at what's happening. What are our next steps? So first of all, we are starting to develop a community of research and practice around software architecture for machine learning systems. And I really invite all of you that are interested in software architecture to become part of this community. And another thing is that we have started to develop empirically validated practices for architecting machine learning systems, and also hope that all of you start contributing to this body of knowledge, because it's software architecture, it's important for any system, but I think for these types of systems, it's really, really important, especially because, like I said, the data dependent nature of these types of systems, but also the fact that you have different teams developing different parts of the system. And so it helps bring everybody together. And with that, this is my contact information in case anybody wants to reach out, and I am happy to take any questions at this time. Marius, back to you.
Perfect. Thank you very much, Grace. That was a very interesting talk. I personally feel very excited because at certain points I saw my own questions, some of my own work. So it was exceptionally interesting. So we have quite a few questions. I'll start by Hamid. So we'll bring you back a little bit to the quality attributes. So yes. Hamid's question is, if some of the quality attributes that you mentioned, like availability, security, even observability and monitorability, are they the same from a development and architecture perspective and the operations perspective when we have the system in production? Do we address them in the same way?
Right. So I am this goes back to what I said about scenario-based development. I am a big fan and proponent of that the way that you develop architectures is based on scenarios. So for example, when I see a requirements document that says the system shall be secure, I just start rolling my eyes, because that means absolutely nothing to me. Usually when people say that to me, I say, okay, let's start breaking these into scenarios, right? Tell me, when you say secure, tell me what you mean by secure. And it's like, okay, I got it. What I mean by secure is that when a user does X, the system has to respond in form Y, and this is how I'm going to measure that. So, like in scenario based. So the definition of the quality attributes is likely going to be the same, right? Monitorability, sure, it's the capability of being able to monitor a system, but the scenarios are what is going to change. So typical monitorability scenarios have to do with, if you think about it, it's monitoring resource consumption, it's monitoring faults, it's monitoring, for example, security leaks, privacy leaks, and things like that. But the scenarios are going to be different. So when I say monitorability in the context of a machine learning system, I'm talking about monitoring model performance. In most cases, I'm talking about monitoring incoming data. I'm talking about monitoring predictions produced by the model. So that is really what is going to change. I think it's the scenarios, and those scenarios are going to drive new design decisions that hopefully one day will be codified into tactics and patterns. And I hope that answers your question.
Sure. Yeah, so we will move on to the next question. Peter has a question. I think it relates more to the explainability. So I think he grasped something on what you said, and then there is the inevitable question of errors in the outputs due to statistical learning. So for example, how do we characterize or explain errors in outputs to the users?
Yeah, no, so explainability, it's one of, so of all the kind of like newer quality attributes, I would say that it is the one that is being the most, I would say, explored. And so what I have seen, and where I think a lot of the research and practice and this is going to, is in supporting not human in the loop, but supporting human on the loop, if that makes any sense. So for example, and some models by nature are more explainable than others. So for example, if I have a model that is based on some kind of decision tree, I could say to the user, and hopefully explain it in a human readable manner, the system reached this decision because, you know, it went through these paths, right? But the idea is that in some cases, you're going to have to say, okay, in as human readable as possible, the system reached this decision because it made these sub decisions, like it followed this path in order to make this decision. And then a human that is observing that system is going to have to say, well, that's, yeah, okay, I get it now. That's it. It makes sense. Or it can say, whoa, that makes absolutely no sense. And at that point, again, going back to the ground truth, it would have to trigger something that says the system is producing results that are just not comprehensible or that don't make any sense. But I think explainability, two aspects to it. One is being able to explain in human readable form what, like you're saying, I think it was Peter, that is statistical language. And the other one is being able to allow the human to react, or I should say the user to react to that, to say, yep, that makes no sense, or yes, this makes sense.
Perfect, thank you. So Julio has also an interesting question. He talks about mixed ML-enabled systems that would include multiple machine learning, different machine learning models. So yes, we can have differences in pace or resource requirements. For example, training a deep neural network or a cart model may take different resources, different speeds, plus an application may have much faster CI/CD cycles than a machine learning model. Yes. So how can we account for these differences from an architecture perspective, when also we don't always have access to the appropriate resources?
No, that is, I mean, that's a very valid question, and I think it's one of the challenges that is going to require a lot of investigation. So first of all is that I think we need to start. I think it goes back to co-architecting. So one thing is the resources that I require to train and retrain a model, and the other is the resources that are required to serve the model, right? And so obviously some models take a lot of resources to train, some models don't take a lot of resources to train. There's also the disparity, right? So usually like video games, right? It takes tons of days and resources to train, but then the model you can run it like on a laptop or even on a phone in some cases. So all those are very interesting questions, but it goes back to co-architecting. It goes back to trying to think about model development and to think about those cycles and to think about what constitute intermediate products. So for example, it could be that when I'm thinking about a system, right, I'm thinking of all the components that go around the machine learning component. So, and those might be able to be, I would say, to be churned forever, at a quicker pace, right? You know, you could have components being dropped every 3-4 days, but for a machine learning component, it can take months to produce a machine learning component. So thinking about what intermediate products look like. So like, for example, what does a proof of concept look like, or what can I constitute half done or sort of done or fully done? And I think that takes from a process perspective, I think that is what the most challenging aspect of it is, the fact that the iterations of their cycles are just so different, and that developing a machine learning component could take so long, and it just wouldn't align. And going back to the question, when you have not only one machine learning component, but when you have multiple machine learning components, then it gets more complex, because you could have, iterations or cycles, whatever you want to call it, that are, days long, and then you have cycles that are months long. Yeah, I don't have a good answer to that. That's where I think a lot of the challenges and opportunities come.
If I may add on that, I think
of course
DevOps may have a good solution for that, because DevOps, the challenges that you mentioned may also be with respect to teams and humans, right? So development paces, handling errors and problems on a smaller scale. So DevOps actually tells us build more modular architectures and try to modularize your development team and your QA team as well to handle problems locally, and then worry about the integration at a later time. So that could be an answer. So Peter comes up with another interesting question, very well voted as well. So he wonders if there is any serious effort from Software Engineering Institute or anyone else to modify the Square standard by ISO, the 25010 ISO standard, to reflect this inclusion of machine learning systems.
Unfortunately, I don't belong to the security team, so I can't speak for the SEI. But there is a very interesting, what is it called? There is a very interesting paper, and it's somewhat recent, by maybe Peter's one of the authors, I don't know. But basically what this team did is that they looked at Square, especially with respect to data quality, and basically it says, you know what, there are so many aspects of machine learning components that are not considered by Square. And by the way, here are some ideas on how I think it has to be modified. So my point is that definitely somebody is looking at that. Whether the owners of Square have acted upon that, I really don't have an answer. But at least I know that there are people that have already started looking at it. I don't have I would have to, maybe I can share with Marius, but it's a really nice paper.
We can share it back in the website. But the answer is that maybe not officially by ISO itself, but people are looking into it. So that's definitely interesting. And Miguel has a similarly interesting question about another standard. So Miguel says, you have shown how ML models change the process of architecting software systems. Even though they are software artifacts, they completely affect how the architecture is defined, for example, in terms of the quality attributes, patterns, and tactics. What happens to the software lifecycle processes? For example, as defined in the ISO 12207 standard, do existing processes change? Do we need new processes?
So again, this is just my opinion, so please consider it just one data point. I really don't think those processes change that much from a high level perspective, because again, machine learning components they're probably the minority. When I look at a system, like a big system, there are not going to be, the dominating components are not going to be the machine learning components, my humble opinion. So what is going to change to me is like the definition of quality. So I think we're pretty, the definition of quality for software in general, I think is pretty well defined, what it means, what quality means. But for machine learning components, it's different. So obviously, defining, for example, quality metrics that would determine, okay, this component needs to be retired. It's in the particulars. I think it's going to change one level down, but not at that level. And I could be completely wrong, but that's my personal opinion.
I just want to add here as well a comment that I agree, and you had a picture somewhere in the beginning with the processes of the different components of a large system, and I think what will happen to the existing processes, they're going to become more hierarchical. So we're going to see the different phases as boxes, and inside those boxes, we're going to have smaller processes like the MLOps process, right? So it's a very distinct process, but it's part of the general system development process.
Right. So one level down, exactly. Yeah. Exactly.
So I think we have time for at least one more question, if my co-panelist may correct me. Heng has an interesting question, and Fuchs has a follow-up on a similar topic. I've lost it. Yeah, I found it. So if you can give us some examples about specific metrics that quantify monitorability and observability, and Fuchs comes back with an extension, how would you operationalize the monitorability and observability attribute? Any intuition on how to architect this? Any architectural pattern that can be leveraged?
That's a very good question, and something that I'm still shocked by our Marius. We matched our outfits today. It looks so nice on the screen. So it, like I said, existing patterns for monitorability and observability. Like, for example, how do you tactics for including observation points inside components, having components expose two interfaces, the call interface and the monitor interface. So those are typical tactics that, again, they still apply. But what is going to be different is what we expose, right? So for example, typical components might expose resource consumption, might expose internal data that is used to calculate some metric, but machine learning components are going to have to expose something else. And that is what we have to think about. So once again, I really think that the patterns and tactics are not going to change at the high level. They're going to change in the details. What, for example, for observability is, what do we expose? So if we let's look at data intensive systems, right? So observability has to do a lot with kind of like with data provenance, right? So the way that I got from data that how it looked here to data that I go, I'm sorry, I can't hear, is because I made these changes, I filtered this and things like that, right? So that still applies quite a bit in these types of systems. But again, what do we expose? What is it important to expose so that this machine learning component is observable? I think, again, it's one level down. At a high level, I don't think a lot of things are going to change. It's one level down.
Mm-hmm. Thank you. So so we're going to take, I think, a couple more questions. Yeah, so the organizer is giving the okay, so that's good. Marin has an interesting question. Marin Litoyer from your university. We're changing a little bit the pace from a technical question to a more philosophical one. So first of all, he thanks you for the very interesting talk. He says AI is very scrutinizing these days by society and quality attributes. He says fairness, transparency, and ethics defined by society, they might change in time as well, right? As we have seen it happening. So he says a lot of initiatives on AI and society. Is there a role for society as a stakeholder of the architecture? Instead of saying person in the loop or person on the loop, can we say society in the loops as a concept?
That is such an interesting and good observation. I think it's a philosophical question, but I think it's very real. And once again, I think we need to think about, again, I know I sound like a broken record, but we need to think about scenarios. So and in these scenarios, the actor, or I would say would have to be, we would have to think about society as an actor in these scenarios. So when I say my system is ethical, let's start defining it with specific scenarios, and what does it mean to be ethical, and how should the system respond when it sees an ethical violation, for example. I really like this idea, but no, yes, it is philosophical, but definitely it's something that I think we should start seeing more as we develop scenarios for specifying what these quality attributes mean. Absolutely.
For me to bring it back to the technical again, Heng answered about monitorability and observability, but how the hell do you measure ethics? How do you measure bias, right, in our society?
Yes, that is very, yes.
It's difficult, but also risky. So
yeah,
it's definitely a roundtable discussion that the community should have.
Yeah.
So I will ask one more question by Ettore from Polytechnique. First of all, he says, beautiful talk. What would be the observations for high quality systems that include machine learning? We're talking about safety critical systems such as avionics. Are we Are we in the process of started thinking about certifications, as Peter and Miguel mentioned, update of standards? What is the process of that? What is the future for that?
It's a very good question, and I know that it is being addressed. Like, I mean, if you Google machine learning and safety critical systems, you're going to find tons of papers and ideas and things like that. It's just so hard. It's just so hard because of the data dependent nature. I mean, I don't think, my opinion, I don't think we're ever going to get to a point where we can certify a machine learning component unless for some reason we have a very constrained domain in which we can guarantee that production data is going to be exactly the same as training data, which is difficult. And if you think about like, for example, safety critical systems, a lot of these safety critical systems rely on computer vision, for example. There's so many problems with that. So, I mean, I don't have a good answer for that, but to me, the only way that you could ever certify one of these components is in very particular and closed scenarios where you can have a guarantee that training and production data are going to be exactly the same. Sorry, I don't have a better answer, but it's just a difficult one at this time because I don't think we're there yet.
That's okay. So I just want to mention that we have a couple of answers to the general discussion. So I would like to mention that for everyone.
Nice.
So Ettore, for example, mentions that in one of their works, they exposed likelihood of internal machine learning computation as possibly a metric or a proxy for monitorability. Joost Visser also gives us a link to a paper on linking ML-related architecture challenges to the ISO quality attributes. So you can find the link in the Q&A for everybody that is interested. There is an interesting question about Ashkan. It's not very technical, but I think it's very pressing for us in the academia and especially the students. So how can contributions to architecting AI-based systems or patterns for ML systems can be published? So based on what they understand, it seems they are just case studies for the moment. So maybe some venues that are more accepting to these kind of works or kind of formatting. It's a very good point, Ashkan. And the thing is that it really depends on. So if you think of if you go down to, for example, what a pattern is defined by, right? Like a pattern, the definition says it's a codification of design decisions that are made repeatedly in production systems. And this goes back to one of my observations. I don't know, it was 6 or 7 or 8, but it's the fact that until we can start seeing those systems, I don't think we can develop like a pattern and say this is a pattern because I've seen it applied in 25 systems. But I do believe that unless we start publishing those things, so at least they define some of the design decisions that can maybe later be mined, we're never going to get there. I mean, you're preaching to the choir, because I am very much in favor of publishing these case studies and industry things and examples, because it starts creating that body of knowledge that can then be mined by others. But I understand that some venues are just they'll say, oh, you only have one case study, we can't publish this. And it's like, I get it.
Well, if I may say, I would say the pattern community have been quite welcoming to this type of initiative.
That's great.
Right?
That's great to hear.
So recently we have been publishing some of the pattern in this community with, I would say, less overhead than we would do in traditional venues. So I think it may be a way to get them out there so that more people can get a look at them, scrutinize them, and then build on them.
That's great.
Perfect. So we are well over our time. Thank you, Grace, for answering a few more questions. Thank you, everybody, for staying back. Once again, I would like to thank Grace Lewis for an exceptionally interesting talk. And I would like to thank you all for your questions and your participation. There are a couple more questions that are left unanswered. So what we're going to do is we're going to forward some of them to Grace, and maybe you can get some answers on the SEMLA website. So once again, thank you everyone for participating.